Hello, everyone. My name is Braecklein, and I'll be presenting on my summer work for the electron. Oh, I even practiced for the electron trap coils for Project 8. So first, let's start with an overview of what Project 8 is. Project 8 is an experiment designed to make a direct mass measurement of the neutrino mass. The way it does this is through tritium beta decay, which will produce the neutrinos, and then we're going to be using CRESS, which is cyclotron radiation emission spectroscopy, to then measure the energy of an electron, and then using conservation of energy, we can back out the mass of the neutrino. So the goal for Project 8 is we're aiming for a 40 MeV sensitivity. And yeah. So let's start with what is CRESS. So CRESS, or cyclotron radiation emission spectroscopy, is a method where we can, using a large background magnet, make an electron undergo cyclotron motion. And once it does cyclotron motion, it will also do cyclotron radiation. So here is, and then we can measure that radiation, the frequency of it, and relate it to its kinetic energy. So here is a plot of CRESS data, where this is a chirp, is what we call it. And the chirp is just as it's radiating due to the CRESS radiation. And then there's scattering events where it will just lift vertically, chirp again, and then scatter event, et cetera, et cetera. And this is the data that we're getting to recreate the kinetic energy of the electrons. So the reason that we're measuring the kinetic energy of the electrons is because we're creating a hypothetical spectra for this right here. This red line is a spectra for if the mass of the neutrino was 0 eV. And then this blue line here is if it was 1.1 eV. So by getting the electron energy results, we can create its actual spectra and compare it to these hypothetical spectra. So if we look at this red line here, this, like I said, would be if it had no mass, which is very different than the spectra that if it had 1.1 eV mass. So the two main differences are the endpoint is shifted over, and then the shape is slightly different as well. So when we get the spectra for the results from CRESS, we can analyze the spectra, and that should give us some information about the mass of the neutrino. Especially, like, for example, if there was one that was 2 eV and we measured it there, we would know that it can't be here because it's been shifted over. The mass can't be 1 eV because it's been shifted over by 2. All right, here are some pictures of electron trap coils, which is what my research is actually doing. And so this is why we care about the electron trap coils. So up here is a magnetic, just like an illustration of the magnetic trap to trap the electrons. And then when the electrons undergo cyclotron radiation or cyclotron motion, they'll be doing it back and forth along this axial path. And so to get those long chirps that I talked about earlier, we need to have the electron trapped for an amount of time, because if we don't trap it, we won't get long enough chirps, which means that our data will not be good enough to construct the energy resolution we want. So we are using these coils to produce this magnetic field on these two sides to trap the electron. Additionally, the shape of the trap matters because if you look at this like flatter trap, there are many different traps that we could use. If we used a simple harmonic trap, the information that we get or gather from these sidebands here, which is just related to the axial motion, won't have any sort of impact on our results. Whereas if we have this flatter trap, the sidebands will give us information about the average magnetic field experienced by the electron. So when we put that into our data analysis, it gives us more information about the energy of the electron. Here is the coils that we wound. This is the inner coils. This is the outer coils. The inner coils are mainly used to shape the field to give us that flatter trap. And during the fabrication of these inner coils, there were some difficulties because this has to go into a cryogenic vacuum. And additionally, we're using very thin wires, which make it very hard to wind neatly. So if you have any more questions about the fabrication, you can talk to me after, but it's basically just a lot of perseverance is my advice. Next, we have to map the magnetic fields from the coils that we wound. So here is the coil, one of the coils that we wound in our mapping setup. To map the fields, we're using 3 Thorlabs motors to control the X, Y, and Z position of a Hall probe. We also have a flux gate to measure the background field. And then in this little corner, you can see a thermometer to give us good precision temperature data. The reason we need good precision temperature data is because the Hall probe operates on something called the Hall effect. The Hall effect is just when you have some sort of wire or current conducting material, and then you have a perpendicular magnetic field, it will cause the positive charges to go to one side and the negative charges to go to the other, creating a voltage across whatever wire or conductive material you're using. Using this equation here, we can calculate the Hall voltage with some constants, a current which would also be constant, and then we have the magnetic field. So in this case, we'd be looking for the magnetic field, so we would just move that over, and then we can back the magnetic field from each position out by measuring the voltage. The issue is that as the temperature rises, whatever sort of object you're using will start to vibrate, which can influence the motion of the charge carriers and change the charge density, which means that as the temperature increases, the Hall voltage will drop, even if the magnetic field is the same. There are other effects at play here, but for the temperature range we're operating at, this is the dominant effect. So we have to have good temperature data to correct for the magnetic or for this effect. Here are some temperature field maps that we made where we have the z-axis and then the radius. The radial 0 here is the center of the trap, and then this is out toward the coils. This plot here is an expected plot versus an actual measured plot from data. So when we tested our coils, this is what we found, which is basically pretty much what we expected, that we have a high range in like the upper 80s, low 90s, which is exactly what we want. So that's the end of the cavity that we'd be putting it into. And then we have a flatter trap toward the bottom. We still have to map more, and that will affect this next slide that I'm showing. This is a different visualization of the data, where this is just a single line representing one of the radii. Again, here is expected, and then this is a measured. So when we do this, we see that they have this sort of shape here, and that it decreases with radius, exactly, or the magnitude increases with radius. It goes lower, but that's because we are using negative magnitudes. So this is exactly what we'd expect. And as we can see, this kind of has a more harmonic shape than that flatter shape we were looking for, but that's because this is just one coil. As we add the other coils, that will help provide the shape. Here are just a list of some of the things I did, and a picture of me working on the coil. With Talia's help, I was able to wind all of the coils on the trap. I was also able to do some calculation or some calibration data sets, updated the analysis of the code to include 3 dimensions instead of just X and Y. I wrote a controller sequence to map out the effective volume of the coil, and I designed and machined parts needed for data taking and presented progress on Project 8 collaboration meetings. Finally, we have why this is important. And it's important because if we are able to properly measure the neutrino mass, then that gives us one more benchmark that we can use to compare our theoretical models against. So if there's a cosmological model that predicts that the neutrino mass would be X value, and we can measure that it is X value, that's a point of validation. And if they disagree, then we know that that model needs work. Additionally, if we look at this graph here, we can see that depending on what the actual mass of the neutrino is, there's a chance we could rule out the inverted ordering or confirm it, depending on the lightest mass eigenstate and then the effective mass that we measure. Finally, acknowledgement slide. Thank you to the whole Project 8, all of the people who fund it, and specifically Talia for all of her hard work with me, and Karsten as well. Yes. The x-axis here, this is essentially just the endpoint. So this is the energy minus the initial energy. So as you can see, it's 0 here because we have 0. So this is basically just the energy spectrum. And then this is being shifted by whatever the hypothetical mass would be. I hope that, I don't know if that fully answers your question, but it's essentially just, this is the energy being shifted over by whatever E naught, which the E naught is the rest mass of the neutrino. Okay, so the green one, this is the exact same type of wire as the other one. It just has well, we were expecting the insulation to be just green insulation, but it's actually like some like green dye of some sort on over the regular Kapton insulation. But the wire themselves are identical in terms of like they're still both 28 gauge wire made of the same copper material, same copper insulation. There's just a colored version here because this particular photo is taken with, I believe there's a light source so you can see a little bit better. When you're actually working, if you look in this area here, or it'd be better to show here actually. If you're using the same copper color, when you're winding against it, it's very hard to tell what one coil is from the other, where switching the spool that you're using makes it very distinctive which coil you're working on. I remember before we made this change, as I was winding this coil, or as I was winding this second coil here, this other coil on the different coil form was also the same color, and I would sometimes lose the wire as I was winding it because it blended in with the copper color here and the Kapton color there. On the graph showing the pull out of the converted order, can you help me with that? Okay. It's a little bit confusing, but essentially this green area here, this is the project 8 sensitivity goal. Also, this is a log plot, so it's not linear, so that might help as well. This right here is an effective mass because the way that the mass works for the neutrino is there's different mass eigenstates. And so that is what the normal ordering or the inverted ordering is. It's basically which one is the lightest eigenstate. But any sort of neutrino is going to have a different combination of those eigenstates. So it's not like the lightest, so you hear the lightest mass eigenstate. The neutrino is never going to have just the lightest mass eigenstate. It'll be a combination of the three. So this is the effective neutrino mass that we're measuring through our experiment. And then this is what ends up being the lightest mass eigenstate based off of that. Because we know the masses relative to each other. So the three different eigenstates, we know how they differ, but we don't know like their absolute mass, if that makes sense. And so this blue band is the inverted ordering. This red band is the normal ordering. And there's a point here where they kind of converge. So if the masses are in this range, we can't rule it out, but if they're in this range, we can then tell.